In the previous lecture, we discussed a concept known as total internal reflection. Now, let's actually apply that concept into the following example. A light source is found 80 centimeters directly below the surface of water. If a single beam of light is to undergo total internal reflection, how far to the right of the source will the ray of light hit the surface of the water before it actually reflects back into the water before it undergoes total internal reflection? So assume that the index of refraction of air is 1.00 and the index of refraction of water is 1.33. So this is water and this is air, and this is essentially our surface, the boundary between these two mediums. So our single ray of light originates at a position 80 centimeters directly vertically below this boundary, below the surface of the water. So this distance, this height is 80 centimeters. So we essentially want to take our ray of light and we want to orient it at such an angle so that none of our light actually refracts and all of that light reflects. So that means in step one, we have to find the critical angle. The critical angle will give us the angle at which our ray of light will refract at an angle of 90 degrees. So when we find the critical angle, we simply choose the angle that is slightly above so that we ensure that all of the light reflects and none of it refracts. So we begin with the following equation, which was derived in the previous lecture. So sine of the critical angle is equal to N air divided by N water, which is equal to, well, N air is equal to 1.00 and N water is equal to 1.33, and that gives us about 0.752. So now to find our critical angle, we simply take the inverse of the sine function of 0.752 or 0.75188, and that gives us approximately 48.9. Now, we want to choose the angle that is slightly above that because the critical angle gives us the angle, our angle of incidence, such that that creates our refracted ray that makes an angle of 90 degrees with respect to our normal line. So that means if we choose a slightly higher angle, let's say 49 degrees, then all of that light will reflect and none of that light will refract. So now we move on to step two. So in step two, we essentially want to apply basic geometric and trigonometric properties. So let's draw the following triangle. So this triangle contains a hypotenuse. The hypotenuse is simply our ray of light. The height of the triangle is simply this distance, 80 centimeters, and the base is the distance that we're looking for. So we're looking for the horizontal distance from our origin, where our ray originates, to where it hits the surface of our water. So we know this angle is 49. This is the angle of our incidence. This is the angle that our ray makes with respect to our height with respect to the normal line. And this normal line is perpendicular to the base. So we have a right triangle. So let's apply the tangent function. So we know that tangent of any angle theta within a triangle is equal to the opposite side divided by the adjacent side. So our opposite side with respect to this angle is x, and the adjacent side with respect to this angle is the height, 80 centimeters. So tangent of the angle theta is equal to x divided by the height, 80 centimeters. So we can bring 80 to this side and solve for x. The horizontal distance that we want to find is equal to 80 centimeters multiplied by tangent of 49, and that gives us approximately 92 centimeters.